Okay, now let's work the other two problems that are associated with section 7.8. And what we'll do is we'll work back off of a figure that we looked at earlier, and we'll put some actual values in there. Now, at the same time, I want you to imagine that, you could do this, right? I mean, you know what an amp meter is, you know what a voltmeter is. Um, we haven't probably used a watt meter in a lab, but again, a watt meter, all you do is you have four terminals and you measure across for the voltage, and then you hook it up like an amp meter. And so you're measuring the voltage across and the current through, and that gives you a watt reading. And then you do a similar thing for the VAR meter, which probably is a little less likely to you're a little less likely to cross paths with. So let's look at what this looks like. So I went ahead and set this up for us, and I put the values that he's given from example 7.5. In 7.5, he says that a watt meter and a VAR meter are connected to a 120 volt single phase line. And everything we're talking about right now is single phase, but in the next chapter, we're going to do three phase power. And then it says that from this connection, and this goes back to figure 711 that we looked at earlier, that the power meter here was reading 1800 watts. And it says that the VAR meter was reading 960 VAR. All right, so he's asking us in the question, he says, what is the in phase and quadrature components of I sub P and I sub Q? All right, this term that he throws out here at us, this quadrature, we're just looking at, this phasor representation, and I don't really know that term. I never used that term before, quadrature, but it's the relationship. We're looking at an angle and we know side opposite over adjacent, and that type of relationship. Bottom line is, what we're trying to do is figure out what the line current is, what the active current is, and what the reactive current is from what we're given. Now, we can do that easily from earlier equations that we used. And so those earlier equations that we had this relationship with, they actually go back to equations 7.1 and 7.2. And those two equations, I have I sub P is equal to power divided by voltage. So I'm going to see if I can figure out what that is. I think I can. It's 1800 watts divided by 120 volts. And that's going to come out to be, for this particular problem, the active current for that particular problem is going to be 15 amps, okay? And that would be the current here would be 15 amps. Okay. Also, I can do that for the reactive current. I sub Q is equal, and this was equation 7.1. 7.2 says that Q divided by E, 960 divided by 120, and that is going to give us 8 amps. So this would be 8. All right, so that's part A, and we solved those two currents. And then if I wanted to know what the line current is, I have to add those as vectors, and that would be, I would be equal, or I squared is IP squared plus IQ squared, or I is equal to this value. Okay. And so, what do we have here? We have 15 squared plus 8 squared. And that total value, whatever that comes out to be, I don't know what those are. I'll plug them into the calculator. But anyway, what I would find out is that would be 17 amps. And that's what this value would be here, okay? So the amp meter at this point would be measuring 17 amps of total current. Now, if I am providing circuit protection to this situation, I need to specify it in terms of 17 amps, not 15 amps, not 8 amps, not just the sum of that. It wouldn't be 23 amps, but it's the vector sum of those two, and it comes out to be 17 amps. He says, what is the apparent power? Well, the apparent power is the voltage times the current, or 120, and the current is 17 amps. And so that's going to come out to be 2,040 volt amps. And then finally, he says, what is the phase angle between the two? And that's going to be inverse tangent of, what's that going to be? 960 over 1800. And if I run that through the calculator and make sure that you know how to do that, do you remember how to do that? You get this value first. And so I would have, how would I do that? I would say 960 divided by 1800. First, I would cut my calculator on. 960 divided by 1800. And I get a value, which is 0.5333, repeating. And then I go inverse tangent of the answer, and I get 28.07, or he rounds it to 28.1 degrees would be that angle there. Okay. Now, did we finish that problem? We did. Okay. Now, we might as well go ahead and knock out this last one here while we're at it. Don't you think? All right, the last problem here, it says a voltmeter and amp meter connected to the inductive circuit of 7-4A give 120 volts and 20 amps respectively. So let's go find 7-4A, and I'll just use that as my figure for us to work. Okay, now let's get rid of some scribbling on here. And 7-4A is a source and a totally inductive load. Right? And he says that a voltmeter connected to this circuit would show the voltmeter would show, excuse me, 140 volts. And he says that the amp meter, which would be here, right, have to be in series, is showing 20 amps. He says, what would the apparent power of the load be? Well, that's really straightforward. That would be S is equal to E times I. This would be the total current in the circuit, right? Whatever is here. And since it's, a simple series circuit, has no parallel branch to it. So I'm going to say 140 times 20. And that's going to be 2,800 volt amps. Then he says, what's the reactive power of the load? Well, let's not just say, hey, I can see what that is. Let's just look at it. And this again is E times I. Well, the reactor or inductor, as we commonly call it, it's seeing 120 volts. And since there's only one path for the current to flow, it has to have the same current through there. So that ends up being, and I said 120, and it should be 140. And so we're going to see that it is 2,800 VAR across there. All right. So what we're seeing here is that this is a total reactive circuit, because all of the power that is absorbed is reactive power. And if you had a VAR meter connected into this circuit, that's what you would see is 2,800 VAR. And then he says, what about the active power? Well, the active power is going to be a 0 in this particular case because there's no resistive elements in there. So, you know, the total thing, apparent power is 2,800 volt amps, but because the current is 90 degrees out of phase with the voltage, it's also equal to 2,800 var. Okay, so that finishes up with section 7.8, those two problems.